So welcome everyone to modeling normally distributed data with repeated measures. Let's just go over some housekeeping stuff. Here's a bunch of links on how to connect with us, and I'll put this in the chat in a minute as soon as I'm done talking. So we have an email address, there's the website that you can go to. Everything that we do is in a GitHub repo, so that you can go there. All the material for this course, as you saw, is in the GitHub repo, but other courses we've done are there. We also have a Zoom channel where we post our meetups. We have monthly meetups, and so they're recorded and they're posted there. This video is being recorded and we'll post it there so you can refer back to it later. We have a Slack channel, which you should have joined, and we'll put information in the Slack channel there. We have a Twitter account, and of course, we're on LinkedIn. Sorry. So our sponsor for this event is Paul Mirage School of Business. We'd like to thank them for their support. We collaborate with their students a fair bit. We have a good relationship with them. So general logistics. So please mute your mic unless you're talking. And then we'll be doing some exercises. And during the exercises, it would be really nice if you were to turn your camera on. It's not a requirement, but it's just nicer because you'll be in a small group of a couple of people. It's easier to talk to people with your camera on. So what's the plan for this evening? So the course is broken down into two sections. One is mixed effects models for normal response, and then we'll take a short break, and then we'll do generalized estimating equations, GEEs, models for normal responses. And the format of each session is going to be basically, we'll go over theory, we'll do an example problem, and then we will put you into breakout rooms and you'll work on an exercise. And then we'll come back from the breakout rooms and we'll go over the solution. So to contact the organizers, the best way is to Slack us. So there is a room called Regression 2021. So if you go to that channel, you can ping us directly. You can do it in Zoom, but stuff on Zoom tends to fly by quickly. So it's a little harder if you're not getting a response from us. The other way is you can reach out to Ryan, John, or Pablo and I directly in Zoom. We put OC Rug in front of our name, so it's a little easier to find. And all this information is in our GitHub repo. So tools for using this course, we have set up Rstudio Cloud. And if you were to go to this link, and again, that's in the GitHub repo as well, and I'll put it in Zoom and Slack. There is a virtual machine that you can set up. You get 15 free hours on Rstudio Cloud. So if you haven't used that up already, everything is all set up there. All the course files are there. You can, it's all been tested. If you're using your personal machine, you'll need to install the following packages. And again, that's in the README in the GitHub repo. So about our instructor. So this is Dr. Olga. She did her PhD in stats at Purdue. She's a professor of statistics at CSU Long Beach. She teaches statistics coarsely, mostly in the master's program, but also some undergraduate courses. She's the past president of the Southern California chapter of the American Statistical Association, and she's authored 4 books on statistics. And the course that we're going over is based off of one of the chapters in one of the books. So the book, so it's called Advanced Regression Modeling with Sas and R. And so this portion of the course, I think it's based on chapter 8 of the book, part of chapter 8. There is a PDF copy of the book in the GitHub repo along with the solution manual. That will stay there for a couple of days. I'll probably take it down Friday or Saturday. But until then, you can, if you pull the GitHub repo, you'll have the book and the solution manual. Please don't share it, but you're welcome to use it for your own personal use. In the GitHub repo is also these slides, and if you click on the link, it will take you to Amazon if you're interested in purchasing it. So with that said, I will pass you back to Dr. Olga, and I'll put the information that I mentioned in Slack and Zoom.
Okay. Thank you, John. So I'll share the screen. Okay. And this is, in a second, I will put it on. There we go, right? You can see it?
Yes.
You can see it. Okay. So, so John, yes, thank you for the introduction. Um, so what we will be talking about today is a normally distributed response, right? Like I do assume that you kind of know the basics of linear regression, normally distributed response variable, but the specificity, kind of the main topic for today is uh, that you have repeated measures within each individual. Measures are repeated either over time or under different conditions. And this picture kind of illustrates the whole, like the whole idea of today's talk, and we will see it again later. Um, so if you plot observations for each individual and connect the lines, that's how it would look like. So in this case, say there are 4 time points of 4 different conditions, and for each individual, the dots are connected. So you have to model it. You have to model it properly. I mean, of course, you can run a linear regression ignoring everything else, right? Like that it is repeated measures, but that won't be correct model. So let me, yeah, I kind of, John already introduced me, but I just want to mention that, I mean, you can see that I've been always into mathematics since I was little. My dad is a statistician, and I kind of always knew that I like math and stats. That kind of proves it. Now, so the schedule, I'll try to stick to that schedule. I have it printed in front of me, so I hope I'll be like uh, following this. And so we will, so next 15 minutes, we will go through the theory plus example, and then you will work on exercise on your own. And I want to mention that in the like where all the files are, programming files that are R files, right? There's a solution, like so there's a file with the like exercise and the solution right away solution. So you can just cheat a little, right? Open that file and look at the solution. But I mean, ideally you would want to program yourself, right? And then we will look at the solution together. We'll take a little break, right? And then we will have another wave of like another approach of modeling, um, kind of the same data sets. Um, and then at the end, we have just additional exercise. We decided not to introduce any like any more regressions at the end, just additional exercise. Now, I kind of do assume some level of intelligence, let's put it this way. And I will be using Greek letters, not a whole lot of them. So this is a complete list of Greek letters that I'll be using. So it's alpha, beta, epsilon, rho, and sigma. And you probably have kind of seen those, like if you study, I mean, you did study regression before, I assume, some basics. So you kind of know beta coefficients, epsilon, it's error, sigma is the standard deviation, right? Rho is the correlation, and alpha is some extra parameters, some, somewhere. Um, we will see it. Yeah, we will, I mean, it will come into play at some point. Now let's talk about it. So what's the difference? What's so special about repeated measures? I mean, why is we can not just run linear regression on it and just be happy about it? So this is what is happening. So we will be looking at measurements that are collected on the same individuals, either at different time points, so that's called longitudinal data, or under several conditions. They're called repeated measures. It can be, I don't know, right hand, left hand, both hands, something, some task, right? And what is happening here is that just if you take a linear regression, right, we always assume that observations are independent from each other. Observations come from different individuals, and all observations are independent from each other. Now, in longitudinal data or repeated measures data, um, you cannot assume that observations are completely independent. They are independent between different individuals. So between different individuals, they're still independent. But within the same individual, they might be correlated. And just think about it. If you have several observations over time within the same individual, if someone had high cholesterol, for example, it's kind of the person would tend to continue having high cholesterol over time, kind of more elevated than others. So it is only reasonable to assume that the observations within the same individual might be potentially correlated. They might end up, like you run the model, they might end up not being correlated. That's fine. But you cannot make that assumption a priori. You have to model them as being correlated. And that's exactly what we're doing here. So the response is normal. So if you plot a histogram, right, of the distribution of y, the response variable, it should be like bell-shaped, normal response. You have a bunch of predictors, x1 through xk, which may or may not depend on time or condition. We will see both examples, like something that you can, like for example, variables like age, um, like typically it's age at the beginning of the study, right? So that will be constant. Say gender, um, some other variables like demographic variables, they won't change over time. But you can have something like, along with cholesterol, you can measure at every doctor's visit, you can measure um, like um, like number of medications taken. So that might change over time. So you'll have a predictor that changes at, it will be different value at different doctor visit. So that's fine to have both, and like time dependent or not time dependent predictors. And you there's nothing special about it. Like there's nothing you need to do um, if it's time dependent or not time dependent. You just throw them into the model. So the observations for different individuals are independent. This is very important. They are independent from each other. At any time point or any condition, if you take two different individuals, observations are independent. But within each individual, the uh, data should be modeled as correlated. So you see, this is also the key. We're modeling as correlated. We're not really stating that, oh, the data are correlated. No, we're saying we're modeling as correlated. And then we just let the analysis decide if the data are correlated or not. I mean, typically the observations are correlated, right? And this is, yeah, this is, I kind of repeated that picture. This is kind of the key picture here in today's talk. Now let's talk further. So the introduce math behind all of that. We will uh, introduce times as t1 through t k. Uh-huh. Did I make a mistake? I did. Um, you see, I used the same k x1 through xk, right? And then also times what t1 through tk. I should have used a different uh, letter here, but that's okay. Well, it's kind of understood. So you have uh, several time points or conditions, different conditions. And the ith individual at time t sub j has a response we denoted by y sub ij, right? It's individual I at time j. And we have all those predictors. They also like x1 through xk are individual I at time j. And what we model, like how we model it. So this is kind of the most interesting part because we write the model, right, as our response will be equal to so beta null, the uh, intercept, right, plus beta 1 times x1 plus and so on plus beta k x k. So we took care of all the predictors, right? Now, what is different from like just a simple linear regression that we know, right, how to fit, is that in this case, first of all, we need to introduce time or condition as a predictor. So it will come into play additively with its own beta coefficient. And also to make observations within each individual, within individual I, potentially correlated, what we need to do, we need to introduce what is called random intercept and random slope. The slope will be in front of time or condition. And those variables, so this is u1 sub I and u2 sub I. Those will be random variables for individual I, right? And those variables will be normal, like u1 I will be normal, mean 0, and variance like sigma squared sub u1. Those are random intercepts. I mean, they are intercepts, right? Because they're just kind of free coefficients, but they're random variables. So that's why they're called random intercepts. U2, they're slopes, right? Because they're like coefficient in front of t, but they are random variables, which are also assumed normal, mean 0, and variance like sigma sub u2 squared, right? That's another parameter of the model. And also we have like our old friend, the random error, right? Which exists in like a simple linear regression plus epsilon sub ij, right? So epsilon it's a random variable for individual I at time j. So those are all different random deviations, right? For each individual, for each time point, will have their own error. And so that's called random error. And like usually for normal response regression, they're normally distributed, mean 0, and variance sigma squared. Now, what is important here is those sigmas, right? We have 3 sigmas, sigma sub u1, sigma sub u2, and sigma. They are unknown, right? They must be estimated from the data, but they are constant. So they do not change. Uh, that's a important assumption of a linear regression, right? It's called homoscedasticity, right? It does not become more scattered, homoscedastic, right? So it's a constant variance model. So in this case, there are 3 variances, but they all assume constant. Also, so these random intercepts that U1, they are independent from each other. U2, they're also independent from each other for different individuals. They are also independent from epsilon, from random error. But you cannot model this U1 and U2 independent from each other. So within each individual I, the covariance exists between U1 and U2. So we assume they're correlated, random intercept and random slope for each individual. they are correlated, and covariance we denote by sigma sub u1, u2. Now, what does this all mean? The beauty of this model is that it's not very complicated. All the effects are additive, what we call, right? We're just adding more variables to the bunch, just additively. It's additive effect. We're not like raising anything to any power or anything, right? We're not making model very complicated. Yet, with this model, it can actually achieve, we can achieve our goals because it will model independent, like different observations for different people as independent and observations within each individual as correlated. And we'll see how it is done. So um, this is how it is done. So first of all, so this is the model, right? I just repeated the model. Now the terms beta null, beta one through beta sub k plus one, they're all called fixed effect terms because there's nothing random about like this first like k plus two actually terms. There's nothing random about those, right? So they're fixed effect terms. They're called fixed effect. The the other three, like I mean, we need only two. U1 and U2 times T. They are random variables, right? And so they're called random effect. So within the same model, you have fixed effect terms, random effect terms. So this model overall is called mixed effects model. I don't know why it's like mixed effects, plural, right? Mixed effects model. Um, but fixed effect and random effect term. Mixed effects model. So with this mixed effects model, which has fixed effect terms and random effect terms, we can actually achieve what we want. And let's see how we do it. So it can be shown. So I kind of omit that part, but if you're interested, it's not very difficult to show. I always ask my students do it. They I teach a course. It's a regular course, undergraduate level course. Students like whine and complain because we study 60 different regressions, but at the end they like it. At the end, um, once they see the big picture, they like it. So my students always derive like all the theoretical part. So it can be shown. So look what's happening. That if you have different individuals, I and I prime, different I is not the same as I prime, two different individuals, then whatever time point you take, J and J prime, they can be equal to each other or might not be equal, but the covariance between two observations is always zero. So if you take two different individuals, either the same time point or different time points, it's always covariance is zero. But if you take the same individual, like individual I, and two time points that are not the same, J and J prime, then the covariance between the observations, so it's within the same individual at two different time points, this covariance actually can be written this way. So it involves sigma sub u1, sigma sub, like the covariance, right? Sigma sub u1, u2, and sigma sub u2. Uh, so those are the parameters of this random effector. And what can we say about this function? We will actually see that later. We will plot this function, but for some specific case, like in our first example, it can behave differently. It is kind of a quadratic form if you think about it, right? Because times are multiplied, so it's more like a parabola. So if you graph this, it behaves like a parabola. It will be like a deep, or it can be upside down. It's actually depends. No, it cannot be upside down because look, the coefficient in front of like t squared kind of will be always positive because it's a variance positive, but its behavior actually depends on the coefficient in front of sigma sub u1 u2 because that's covariance. It can be positive, can be negative. So then how this parabola behaves will depend on the coefficient of this, like the covariance between random slope and random slope and random intercept. But in general, how can it behave? I mean, typically, think about it. Over time, the uh, covariance should, I would say, it's either decreases, but we will see. We will see examples. We will see. Actually, we will talk about it much more today. But what is important is that you see, with the very simple model, it's very simple, additive model, right? We eh, we we achieved what we wanted, right? The covariance between different individuals is zero, right? But the covariance between the observations within the same individual, not zero. It will be zero only. Look, it will be zero only. All these three sigmas are equal to zero, meaning that like there are no random effect terms altogether. Uh, there is one node though. Like if there is no random slope, there is no u2, only u1. Then this covariance, look what happens. This covariance is constant, right? So that sigma sub u1, u2 is zero because u2 does not exist. Sigma sub u2 squared is also zero because u2 like does not exist. But the covariance uh, between two observations within the same individual will be constant. It will be equal to the variance of u1. And I mean, that's what you see. Like if you can actually plot the data, for example, if you see that the variance covariance doesn't change, then it's like, oh, it's likely that the random intercept just should not be in the model. It's only the random slope. So it is kind of a natural reduction of the model. It can happen that of these two random effect terms, you you will just really need only the random intercept. Let's move on. Now, what I will do, I will look at this um, model only from the point of view of the distribution of the response variable. Like we have a response variable y. What is its distribution? And um, so then from everything we have seen today, the distribution of y is normal. We know that. What is its variance? I mean, sorry, what is its mean? Its mean is only the, sorry, its mean is only the fixed effect terms, right? It's that linear sum because um, all these random uh, terms, they all have mean zero, right? So the mean of y is a fixed effect term. Now the variance of y is, it can be also derived, is equal to this, right? It's kind of, how to see this? It basically this, in this covariance, if you take the same y, right? So basically times are the same. So you have twice uh, the cross terms will be just two t's, right? Times sigma sub u1 u2 plus sigma squared sub u2 times t squared, but plus also the variance of epsilon of the random error. Keep this in mind because this is also important way of looking at this model. And in the second half, we will be uh, modeling. We will be looking kind of, again, we will be looking at like a different type of model, but still we will be talking about the distribution of the response. Now, the parameters of this model are k plus 2 beta coefficients plus 4 sigmas. So these are all the parameters of the model. They have to be estimated from the data. And this is kind of the whole idea of this um, regression. And we will talk in a second about it. So how would you write the fitted model? The fitted model is, it's always the estimated mean of the response variable. And that hat means is like estimated, right? Estimated mean. You'll run the model, you'll get estimates for beta coefficients. So will be beta null hat plus beta 1 hat, beta k hat, beta k plus 1 hat. So you'll just, sorry, you just plug those in, right? And this is your fitted model. But also, don't forget that you have 4 more parameters of the model. Because basically, essentially, when fitting a model, you're saying that the distribution of the response variable is normal, the estimated mean is so and so, and you should also say what the estimated variance is. And in the estimated variance, you'll need to estimate 4 sigmas. So you also need to talk about the values of the like this sigma, all 4 sigmas. Uh, when we run R, we will see that it doesn't really estimate those like the variances and covariance what's in the theoretical model. What it does, it estimates standard deviation, right? It's like sigma sub u 1 hat, like without squared, right? It's a standard deviation. Sigma 2 hat, so that's the standard deviation of u2. And instead of covariance, sigma hat sub u1, u2, it estimates rho, the correlation coefficient, which we know is actually the ratio, right? It's the covariance, right? The covariance divided by the product of standard deviations. So it is, in a sense, it doesn't matter really, right? Because we can always restore anything, like um, whatever R estimates is a complete information. We can always compute what the covariance is if needed, what variances are. And also it estimates sigma. So it's standard deviation of the error term. But that's okay. I mean, it's like, it doesn't matter, right? Because it's all, we can still, we can still write the estimated variance if needed. Right? Estimated variance of Y. Now let's talk about it. Like, why would we fit a regression? Well, there are 2 major uses of regression model. One is interpretation of the estimated coefficients. Why do we need it in general, like from philosophical point of view? Because we can right away see, like, for example, if a group like intervention versus control is your predictor, you can see right away if like intervention worked, right? Like if people in the intervention group did much better than the control, or if, like, say, women are more prone to something, or m- men are more at risk for something than women. So when you interpret those coefficients, you see the significance, right? Like, and it's not only what predictors are significant, but also by how much, in a sense. And also, the second major use of regression would be for prediction. You want to predict, like, say, you got a bunch of um, predictor variables, right? Certain, like, say, you got a new person coming in, right? And you can, like, say, new person applied to the university. You can collect the information about the predictors, right? Plug it into the model, and it spits out the prediction. So then you know, like, what the response will be, kind of what we estimate the response will be for that individual. Now, how do you interpret fitted coefficients? Fitted or estimated, the same thing. As you know, because I kind of assume that you have this knowledge, that the predictors, when we use predictors, they can be either continuous, or if they're categorical, right? If they assume values like 1, 2, 3, uh, then you create dummy variables like 0, 1 variables, indicators of uh, certain level, right? Like, for example, if you have, I don't know, say race, black, white, Asian, for example, then you will have indicator variable for black, indicator variable for white, right? And Asian, for example, will be the reference, right? It will be 0 for Asian, and then 1 for black. That will be one predictor, and indicator for white. That will be another predictor. So if you have a variable with 3 levels, you will need to introduce 2 um, indicator variables and put them into the model. So all your predictors can be of only 2 kinds. They can be either continuous or 0, 1. So if x1, for example, x1 is continuous, how do we interpret the estimated coefficient, like the slope in front of x1? Well, you can just think about it. This is kind of math behind it. If you take the estimated mean response for x1 plus 1, so you're increasing x1 by 1 unit, and then you subtract the estimated mean response for like x1. What happens is, well, you can just write out it honestly, right? Everything cancels except what is left is beta 1 hat. So what is the meaning of this beta 1 hat? Beta 1 hat shows how the estimated mean response changes, right? It can increase or decrease depending on the sign of beta 1 hat. uh, how it changes if you increase x1 by 1 unit, right? So that's exactly what it is. Beta 1 hat represents the change, increase or decrease, in the estimated mean of y, right? This is very important. I always like beat my students to death, kind of, because it's exactly what it is. It's hat means estimated, e means expected value or mean, and y means response variable. So that's a must. Estimated mean response, so estimated mean of y for a 1 unit increase in x1. X1 is always increased by 1 unit, right? Because we go to x1 plus 1. But estimated mean can change. It can increase or decrease depending on the sign of beta 1 hat. And also, what is very important is that we kind of assume that other parameters have not changed, right? They stay the same. Uh, so that's what, technically speaking, you should be including, right? Provided all the other variables are unchanged. And the other type of predictor can be 0, 1, right? Like male, female, for example. So then beta 1 hat will be interpreted as the difference, not the change, but the difference. And you're looking at the difference of the estimated means of y for, like, say, males and females, right? For x1 equals 1, it's called like upper level, x1 equals 1, and x1 equals 0. So you are really comparing like all males to all females. And um, and it's a change because, like, we're not aiming at changing the gender here, right? Like, we're just comparing 2 groups. So that's the difference between the estimated mean response of 2 groups, males versus females. And if you compute that difference, so when x1 is equal to 1, it will be like beta 1 hat times 1. When x1 is equal to 0, it will be beta 1 hat times 0. So again, everything cancels. Um, and what you have left is beta 1 hat. So in this case, beta 1 hat interprets as the difference of the estimated means of the response for x1 equals 1, x1 equals 0, controlling for the other predictors. That's how it's typically said. Like, it means that they're unchanged, right? Controlling for the other predictors. We will see specific examples, like how, like, in our examples, how they're like, how you word it in every particular case. And prediction is like you have a set, like some specific values, and you also notice that you also have to have a you have to say at what time point you want to predict, right? Because time now is a legitimate predictor. So you have to say like at 3 months into the study or at 5 weeks into the study, right? And the time is actually And this time is interesting that if you collect data at, say, 0, 1, 3, and 5 months, this time comes in continuously, right, as a continuous predictor. So you can even predict at some time point that is not when the data were collected. You can, for example, ask for like 2 months, for example. Data are collected at 0, 1, and 3. You can say, hey, I want 2 months. You can just plug in 2 months, 2 months into the study because it comes in continuously. Now
Sorry,
let's look.
Olga,
Yes,
sorry, can I ask a question?
sure.
In the formula for variance, the time appeared as a quadratic term, as t square, right?
Hmm. Hmm.
So, is it still okay to call the model as homoscedastic because the variance is not constant?
No,
So,
no, no,
is
no.
it
It's not
homoscedastic
homoscedastic.
still?
It will be homoscedastic only if the random slope is not there, right? If the random slope is not there, these middle two terms will disappear. If U2 is not present, then these two like middle terms will disappear. You have only sigma squared U1 plus sigma squared. That one will be homoscedastic. And you will be able to see if you plot the uh, observations. We will see it later. You will see that it's like the variance doesn't change. It stays the same over all time points. Uh, but if you are
Okay, thank you.
introducing random slope, then the variance changes. The variance changes. Let us look at, let us work through this example because in this example, I plot this variance so that we can see what's happening visually, which is like really good. We'll be learning a lot from the pictures. So let's look at this. Kind of incidentally, my examples, I believe, are all kind of medical, kind of have to do with like health sciences or medical. I don't know, just kind of historically, because my actually background is I did some work with, like, I mean, if you look at my CV, I did quite some work with, like, here and there for medical people, kind of historically. But also, um, it's it's a simple enough example. Like you don't need to introduce any like explain terminology or anything. So it's kind of easy to understand. So I kind of like those examples. But in my book, I think you can find other examples, not just necessarily medical. Okay, so let's look at it. So in a clinic, doctors are testing a certain cholesterol lowering medication. Patient's gender and age at the beginning of the study are recorded. It's typically if you record age, right? Then it is not like it's not going to be recorded at every visit because there's no. It's like it just increases linearly, right? So if you introduce age, then it's in the beginning of the study, and it will not be time dependent predictor. Gender is also typically like you just record once, right? Even though, like, honestly, I did do like because I do a lot of work with health sciences people, and I saw a variable. It was like gender before the study begins and after, and it wasn't about gender change or anything. And just out of curiosity, I ran them to compare, and like 6 people changed their gender while the study was going on, and it wasn't like anything related even to that. But anyway, so typically gender and age just collected once at the beginning. Now, so say 27 patients, 27 just because it's not small, not large data set, so it kind of fits on one page. Now, this low density lipoprotein, like LDL, that's kind of bad cholesterol, right? Uh, will be measured at 4 time points. So it's called baseline, like at the beginning of the study, baseline, and then at 6, 9, and 24 months visits. And it will be the same for each individual, right? It will be measured at this exact time points, even though remember time comes as a continuous predictor, so you don't necessarily have to have like exact the same times for everyone. Now we will use the data set, I'll click on it in a second, to develop a regression that will relate LDL level to this predictor. So predictors will be very simple. So it will be just gender and age. They're not time dependent, right? And then also months, like time, it will be months in the study. It will assume values 0, 6, 9, and 24, but we will be using it as continuous predictor. So the data set looks like this. Now, this is important because that's we will be working with that. This is, look what happens. This data set is called short and wide data set. Because each row is just a single individual, right? Each row, I just assigned IDs 1 through 27, gender, age, and LDL at time 0, LDL at time 6, 9, and 24. Now, what we need to do, we will actually be making it, turning it into a long form data set. Because what you need to do, we will do it in a second, but basically we will turn it into a long form data set, which will contain variables like this. So it will be, ID will be repeated 4 times over 4 time points. Gender will be also repeated 4 times for this individual. Age will be repeated as like 50, 50,
Hi,
50.
Professor Olga,
Yes.
I ask a question. Because you mentioned the time is 6 months, 9 months, and 24 months.
Yeah.
Actually, age should be changed.
No, it's age at the beginning of the study.
But the age at the LDA 24, the age should be increased too. For example,
No, I mean, you can do it, but it's not, no, it's age at the beginning of the study, that it's collected once. At the beginning of the study, person is 50 years old. Potentially, you can actually do this, right? Like, I don't know, 50.5, like increase the age.
Yeah.
But it's not going to add any new, like, meaningful information because it increases proportionally to time. So it's not really, it's not, I mean, you can do it, but it's not going to be anything useful, kind of.
Can I ask a dumb question?
Yes.
Why isn't including a constant in your relationship with time? Why is that a bad idea? Because you said that it's not useful. So could you elaborate on that?
Say it again.
So you just said if we add a constant to our variable in time, for example, we allow age to change because technically it is changing in time, but it's changing by the value in time. So really just we're adding the same value. Why is that a bad idea?
It's
in a
not
mixed effects model.
If you do it mathematically, it's not so basically it will increase proportionally, right? It will increase proportionally. You can do it. I mean, you can do it. It's fine, but it's not 9. So it's like
so you're saying it adds a scale factor that doesn't necessarily represent the meaning of the variable, is what you're saying.
Yeah, just think about it. So that would be like 52 here.
Okay.
It is, so you're regressing on something that increases linearly, right?
Right.
I mean, you can do it, yes. But it will, how would you then interpret the fitted coefficient?
Well, actually, that is the second question I had is, will you be showing an example of how we interpret these? Because I'm not sure.
This, I mean, because I remember I've done it before, like long time ago. If you regress on something that increases linearly, because look, also what we need time variable, right? Which will be like 0 in months, say 6, 9, and 24 months. So there's a linear dependence between age and time, right? And you're including both in as your predictors. So that's your predictor should not be that linearly dependent, and they are.
Okay, so it shouldn't be a perfect correlation, is what you're
Yeah,
saying.
it's kind of because age and time would, in a sense, be perfectly correlated. And you will be regressing. So it means that you'll need only one of them, in a sense, not both.
Gotcha.
But we do want both, right? In our model. So let's change back to like this. And then like say LDL. So what I'm doing, I'm showing you like in a second, we will turn it into a long form data set. And that's how it would look like. So LDL at time 0 is say 73. So basically we're transposing this short and wide data into long form data. 80, 85. And then you'll have like a second ID repeated 4 times and so on. It will be a very long data set. And that's why it's called long data set. But each row is each individual at different time points. So like if this is a 27 by something, 6 by 7, right? This is 27 by 7 table. This one will be 4 times 27, right? That's how many rows it will have. 27 times 4. It's 108 rows and 5 columns. So that will be a long form data. So this is what we're going to do next, actually, before we run. Like it's part of the code. So what we want to do, we want to regress, right, LDL level on gender, age, and months into the study, the time. So this is the code, and if you want, I can run it for you. But basically, this what this code does. It reads the CSV data set, which I just showed you. Then it creates a long form data set. The way to do it is with the Reshape2 library, right? It should be installed, right? I have it installed. And then the function melt, you have like id.vars. It tells you which variables will be like repeating, like what we just saw. ID will be repeated, right? 1 1 1 1. Gender will be repeated, age will be repeated. What will not be repeated is LDL. And we will create, I'll show in a second how it looks like when you run this. LDL months, it will create a new variable. Let me right away, run the code. Let me run the code because it's really better be showing what I'm doing. So here I'm running this Reshape2. And how does this look like? It's a long form data. Long form data. It looks like this. Let me just give me a second here. So it well, it is actually sorted. It's not 1 1 1, right? It is sorted like 1 through 27, and then again 1 through 27, 1 through 27, 1 through 27. It's 108 rows total, but they're not grouped by IDs, but they're grouped by so what we're doing, we want to create this like this LDL variable, right? It actually did put it did create LDL variable, right? It did create LDL variable, but the only thing it didn't do, it did not create time variable. So time, it should be like a month or something. It should have values 0, 3, like 0, 6, 9, and 24. So with this, like variable name equals LDL months, what we did it because it will have it will know to say like our variable name is LDL null, like in the original, in the short and wide data set, LDL null, LDL 6, LDL 9, LDL 24. So that's what this procedure does, right? It just puts the variable name in the column. And for us, this variable name actually is what? It's LDL and then months. Months, which is 0, 6, 6, 9, or 24. So what we need to do, we need the last thing is to create a variable called months. So basically strip this LDL months of LDL, right? Just leave the digit 0, 6, 9, or 24. And this is, I mean, the easiest way to do it with if else, right? So if this LDL months is equal to LDL 0, then the variable months will be equal to 0. If it is equal to LDL 6, then the months will be equal to 6. Otherwise, it will be like LDL. So if it's LDL 9, then it's 9. Otherwise, 24.
Dr. Olga, can you
Yes.
make your request to make this full screen? Maybe it's a little difficult for the participants to see. That might be a little better.
Here. So it's let me here. So yeah, if you just run this melt, right, melt function, it what it does, it takes the variable like all the other variables not listed in ID variables, right? It will turn them like it will create two variables, right? One is what we called LDL, which contains LDL levels, what we want, but the other variable will just contain the names for that variable, and that names we need to turn into months variable. So that's what we do separately. Now, this months variable, we can make it part of the long form data set, but we don't have to, right? Because in R, they can live outside of a data set. So we don't really care if like months is by itself, right? A variable by itself. So I can run this. Say I can run months, and I can show that how months look like this, right? There will be like zeros and then sixes, nines, and 24s. And after that, we can plot a histogram. We can plot a histogram, and the long form data is fine because all we need is just to see that it's a bell-shaped curve, like a normal response, not like right skewed or something. So that's good enough. We can also run, like I have a Shapiro test, just it will tell you. So basically, p-value, a large p-value larger than 0.05 tells you that it is normal. And in this case, kind of barely normal, but that's okay. And then we run the model itself. We run the model. I'll go back to, I will go back to the slides in a second. We feed the model. This is how it looks like. It's like a lot of information. And on the slides, I'll tell you what to focus on because it does produce all the values we need. And yeah, let me maybe go back to the slides. So yeah, once we created a long form data set, we created months variable. Then we plotted the histogram, right? Kind of barely made it, but that's okay. Good enough for our purposes. The normality test, the null is always that the distribution is normal and the alternative is non-normal. So we want p-value to be larger than 0.05 to accept the null, right? To say that distribution is normal. And when we feed the model, now this is what is important. What I have here, I have some kind of a control because, you know, these models do not necessarily converge, not always. So the best way to make them converge is to try control equals LME control. I don't want to elaborate on that because, you know, there are different options that you can use. I mean, if you want, if you're really into it, you can explore this, but I just want to move on. So on the output, what we're looking for something that says random effects. Those are our sigmas, right? So this is the intercept is random intercept. This is sigma sub u1. months is the random slope. So this is 0.886 is sigma hat sub u2. Residual is the standard deviation for the random, it's a random error. It's a sigma, right? So sigma hat is equal to 8.358. And this it's correlation coefficient, right? Estimated correlations, rho hat, between the random slope and random intercept. And it is negative. And we will see in a second what that means, actually. A negative correlation coefficient. So that's a rho hat estimated as negative 0.812. Then there is also a fixed effect in the output. Of all of those, we really need to look at the value column, which are our beta null hat, like beta 1 hat, beta 2 hat, beta 3 hat. And we also kind of should be looking at the last column. It's a p-value which will tell us which predictors are significant, because some of them might not be significant at all. So the significant ones are those with the small p-value. You're kind of not interested in the p-value for the intercept, because who cares like if intercept is significant or not. But for like predictors, it's important, because basically in this case, all three predictors are significant. And it means that like males perform differently from females. We will explore that. Age also matters. And then months into the study also matters. Now let's see what this all means, like how to interpret all this. Well, first of all, you write down the fitted model. A fitted model, it is the estimated mean LDL level, right? You just like see all this, the estimated coefficients, 94.827, blah, blah. You just like dutifully put that into the fitted model. So that's the estimated coefficient times male, because that's what we're using as gender M. So it's indicator of a male, and the female is reference category. Age is continuous and months is continuous. So it's like plus the estimated coefficient times age, minus estimated coefficient times months. And also, don't forget that you need to write down the estimates for the other 4 parameters. Do not just ignore those, because that's part of the model. And so here is like all the p-values are less than 0.05 here in the last column. So they all are significant predictors. And so let's talk about it more. So what does it mean? So it means that like let's talk about it. So the distribution, the LDL measurement has normal distribution. The estimated mean is that one, right? Like from the fitted model. The variance, estimated variance. You can also write out what it is, plug in all the estimates. And that's what I did. I kind of simplified it. That's a parabola. And out of curiosity, I plotted that parabola. That's what actually we have like next in the code. I mean, we normally we don't do this, like when we do regular analysis, but just to illustrate what's happening. I just plotted it as a function of t goes from 1 to 30. And see what happens. So this is how it looks like. Our study actually goes from 0 to 24 months, right? It's from 0 to 24 months. And so what does it mean? It means really that the variance decreases. It decreases. So it's the beginning, it's like some variance, right? And then over time, we should see the decrease in the variance. So the data should become less and less variant. And this like we see this behavior like because the It's actually because there is a minus sign here, right? Because the correlation is negative. The estimated correlation is negative. That's why we see this behavior. And so what I did next, I plotted, this is called individual profiles. So 27 lines. So for each of the 27 participants, right? Over time, the lines are like the dots are connected, the measurements are connected within over time, right? Over 24 months. And you can see that the variance indeed decreases over time, kind of the smallest variance at 24 months. How to plot it? This is, we're not doing this like in the exercises, plotting, but you can plot it. What I did is I took the original short and wide data, cholesterol data. I transposed it because it needs it. I mean, I can explain more, but you can just run this code. And then I removed, there was like a gender, like ID, gender, and age. I removed first 3 rows. So it only left with LDL observations. And then I just plotted with matplot. I removed axes altogether. But then I added like the ones like custom made, because I really want like 0, 6, 9, and 24 showing. And then y-axis as is can be added. If you want, maybe during the break, we can go line by line, but it's not difficult, or you can do it yourself. So you can see that the variance indeed decreases over time, and that's what we see in the model. Now, how to interpret? 2 things left, and we're running fast. Okay, that's okay. We're not on schedule, but we will catch up. That's fine. So we will. So 2 things left: interpretation and prediction. How would you interpret? Well, all 3 predictors are significant, so let's just interpret each of them. So gender, age, and months. Gender, meaning you're comparing men to women, right? And in terms of the estimated mean LDL. And for men, it is actually 29.811 points smaller for men than for women because of the minus sign, right? So male have lower LDL level than females. Now, age at the beginning of the study. With the 1 year increase in age, right? Because it's a continuous predictor, we're increasing age by 1 year. The estimated mean LDL increases by 0.92 points. So it means that it's like if the person at the beginning of the study, if the person was like 1 year older, right, to start the study, then the estimated mean LDL would be larger by 0.92. And months into the study is for every additional month in the study, right? Because time is continuous and it is in months. And so we use this as a continuous predictor. So now we can forget that it is 0, 6, 9, and 24 months. Is we increase time by 1 month. So with every additional month in the study, the estimated mean LDL, that's a must, estimated mean LDL, what happens to it? What happens to it? It decreases, right? Because it's a minus sign. It decreases by 1.096 points, whatever the units are. And we can actually see that on the picture, right? The LDL, the general trend over time. Look at it. Like if you're just looking at this whole thing over time, like see the general trend. The general trend is downward. So over time, it decreases and it becomes less variant too. Now, let's use this for prediction. Like, for example, you got a new patient, 48-year-old female, and we want to predict the level, like LDL level at 3 months into the study. And 3 months, remember, 3 months is not part of the study, like data collection times, but that's fine. At 3 months, we can just predict, right? You just like plug everything in. It's a female, so it's a 0 for gender, age 48, 3 months into the study. So we expect to see like LDL level is 135. And in R, what you do, you say predict, function predict, then object is fitted model, and you put in like a new data, which comes in as data.frame, gender equals 0, age 48, months equals 3, and also you need to say level equals 0. This is a little tricky. So basically, level equals 0, meaning that for random effect terms, for U1 and U2, you plug in values 0. Because potentially, I don't even know when, but potentially you can just plug in any number, right? Like you can fix U1 and U2 at certain levels. Those will be conditional distributions, conditional uncertain values of U1 and U2. But if we don't want that, and we don't want that, we just want to plug in like the mean values, zeros. And that's what you say, like level equals 0. That's what it means. Now, so we will do the exercise next, but let me do one thing. Let me ask you, why do we do this? Like, I mean, why is it, I mean, what, like, so basically you have your data set. If we just run a general linear model on it, assuming that all observations are independent from each other, so we will just run the model with fixed effects. We can stick in time, like months, into the model. That's fine. But we will just have epsilon, random error there, without U1 and U2. Why is this model incorrect? Like why we should not be running this model? I mean, technically speaking, the model will run, right? The response is normal. The model will run. But it will be inaccurate model. So it will estimate beta coefficients. It will estimate sigma, right? A parameter, sigma. But it will not estimate all the other sigmas. And it means that the estimates of beta coefficients and sigma, they will be not very accurate. They might be even so inaccurate that the sign might change even. So by estimating all the sigmas, right, we estimate 4 different sigmas here, right, in this model. And notice that when we interpret or use for prediction, the model for prediction, we're not using sigmas at all, right? We kind of forget about all these estimates of sigmas. We're working only with the fixed effect terms. But by estimating all these 4 sigmas, we took care of, like, we get better estimates of beta coefficients, more accurate estimates. I have seen actually, like if you run, like examples, when you run a wrong model, the coefficient even changes sign. Like you think that males do worse, but in fact males do better, for example. Okay, so then this is why we need this model. Okay, now talking too much. Now this is your, technically speaking, you have only 5 minutes, but you probably need more than that. This is your exercise. Let's look at it quickly together. So there's some physical fitness course, and so it will be participants' gender, age, again in the beginning, but it's not in the beginning. You will see in a second. It's just age. Because what happens here, the data are not collected longitudinally. Let me click on that data set. The data are collected actually at different conditions. And that's fine. That's fine. You just say condition 1, 2, 3, and use that condition as continuous predictor. So you have age, you have so there is oxygen intake and runtime and pulse at 3 different conditions. So conditions are, let's see, so the condition number 1 was 3 different conditions. The first is on a treadmill, second one is indoor running track, the third one is outdoor running track. And so it is, so age, look, gender and age are not time dependent predictors, but you are modeling pulse, I believe, right? So then oxygen and runtime will be time dependent predictors. And that's okay, that's fine. So you will be modeling pulse, right? Does it say here? Check that pulse is normally distributed. That's what you will need to do. You'll construct a histogram in normality test, not tests, just test. It's a Shapiro Wilks test. Then you will run the random slope and intercept regression model, mixed effect model, and write down the fitted model. You will interpret which predictors are significant, right? You will discuss which are significant and interpret only significant predictors. And then you want to run it, like you want to predict for, say, 36-year-old woman who is running on a treadmill, so it's condition 1, and her oxygen intake and so, and runtime is so and so. Also, so this is kind of the answer. So let me very quickly, if you look at, so basically what you need to do, you need to find this data set, fitness, mixed effects. So then all your, like the questions are listed here. And what I did, I already created the long form data for you because that takes time. And especially that you have 2 time dependent predictors. So you have to like use that melt function twice, do them like separately, and then you do cbind together into one long form data. You might want to, like, if you have time, study this, like exactly what was done, but that's what you do separately if you have time dependent predictors. Okay, so you work, John, all yours. You want to like put people in groups?
Yeah, so Ryan is going to give them a quick demo of the Rstudio cloud where they can just find their files, and then he'll move them into groups.
Okay.
Great. All right, John, if you don't mind, can you repost the link to the Rstudio cloud environment, please, in the chat?
I will do that.
Thank you. Okay, so everybody, obviously you can use your own computer if you'd like, but one nice thing is about Rstudio Cloud where we've configured the workspace, copied the files over, and installed the necessary packages. So this is what it's going to look like when you go to the link that John's posting there. Occasionally, Rstudio
screen share just dropped.
Excuse me, was there a question?
I think your screen share just dropped.
Thank you. Let me check. Thank you, Pablo. I need to share the screen. Okay, here we go, everybody. Can we see this? When you go to this link here, you'll see this environment here. Sometimes Rstudio will go to sleep. So if you have this running in the background while Dr. Olga is talking, it might say, we need to refresh. No problem, just click the button. It'll take a few seconds, it will spin up. You will see this kind of Rstudio environment here. If you look at the files pane here on the right side, you'll see all the examples. And I think we're working on the fitness mixed effects exercise. Is that right, Dr. Olga?
Yes.
Great. So you'll click into that folder, and then you can click on the don't click the solutions. That's
you
the
can
answers.
Actually click on solutions, but that would be cheating.
That would be cheating. We don't want to do that, right? Okay. So click on the exercises without the solutions, and you will see the file, just like Dr. Olga talked about. You'll see some code up here you can run, and the questions are down there. Sorry, the other important thing here is in your Rstudio environment, please click Save a Permanent Copy before you do all the stuff I just said. That will save it to your personal workspace so you have access to it after the course is over. So please click this first, and then you can go at the exercises. And go ahead and ping us in the chat if you have any questions. All right, so I think now we're going to put everybody into breakout rooms. There'll be about 5 people per room, and then we'll call you back in about, what, 5 minutes, Dr. Olga? Is that?
Well, 5 is, I don't know. Let's give them like, well, I was like 20 minutes late, right? But Like, let's, I don't know, 7 minutes. That's okay, right? I mean,
Let's pull them back about 8 o'clock. That's about
8 o'clock.
Okay?
That's fine.
Yeah.
10 minutes.
Okay, sounds great. All right, good luck, everyone. We'll see you soon.
And we will continue. So basically, all you had to do is to write this much piece of code, right? Like not a whole lot of lines that will answer all your questions. And so I'll just close the whole thing. Yeah, I'll close the whole thing because it's not. I'll open the slides. I'll open the slides. That was our example. So yeah, so this is the answer to what you were supposed to do, right? So you plot the histogram for the pulse, and it looks like this. It's kind of not really very normal to the eye, but Shapiro test says that it's normal, right? P-value is large, 0.6173, so it's kind of very normal. So that's good, right? So we can run the model. And that's what we do, right? Just copy and paste and change variable names. I do want also control, but it might not be needed in this case, but I just like routinely stick it in. Now, in the output, you should find a random effect like estimates, right? And fixed effects. We need the values, estimates of the beta coefficient and the last column, p-value, to see which predictors are significant. And in this case, look at it. So the p-value is small only for gender, right? Not age, but for oxygen, not runtime, and for condition. So the significant predictors are gender, oxygen, and condition.
Can I ask about the t-value?
Yes.
So in linear regression and interpreting for business cases, you can take the t-value, modify it just slightly, and make very good plots for business cases. Is the formula for t-value for mixed effects models similar to the formula for t-value for linear regression, or are they completely different?
So
like, is it
t-value
conceptually
basically
similar?
it's a t-test, right? I'm sorry, this is a t-test, right? This is a p-value for t-test.
So it's still a t-test. Okay.
It's a t-test. Yeah, it's a t-test. T-test, you know, like sometimes it's called z-test, sometimes it's chi-squared test.
Right.
Because it's easy to, like, it's just z squared, it gives you chi-squared.
Yeah, what I was worried about is if you make this a bar chart, you can essentially, and the t-value is nice in that it's uniform over the units. So it's like
yeah, you can do it. Yeah, if you want. Yeah, we usually look at p-values, right? Just like to decide.
Yeah, but you could also do a t-value.
Yeah, you can do this. Yeah, you can do a bar graph of t-values. That's fine. It will tell you which one is more significant than others.
Right. Which is why it's good in business cases.
Yeah, no, it makes sense. Yeah, but it's just the t statistic for a t-test.
Right.
That individual beta coefficient is equal to 0. That's the null, and not equal to 0 is the alternative. So that's why we want small p-values. We want to accept the alternative, that the beta coefficient is not equal to 0. If it's large, meaning that it's as if it's just equal to 0. So runtime does not come into play. You can just multiply it by 0 in the model, essentially. Okay, so when you write down the fitted model, you just honestly write down all the estimated coefficients, right, in front of like the corresponding predictors. And look, it says gender male, meaning it's a male, like female is the reference. Age is continuous, oxygen continuous, runtime continuous. Condition is also continuous in this case. Like it's 1, 2, 3 though, but that's okay. It's continuous because in this model, we just use it as continuous. That's okay. And then don't forget all the estimates of these 4 parameters, right? All the sigmas, rho, they also should be specified. We do not use them later, but we do need to specify them in the fitted model. because otherwise it's incomplete information. You're saying the response is normal. This is the estimated mean. And where is the estimated variance? Like, where are the estimated all the other parameters of the model? So technically speaking, you should be mentioning those. Now you use for prediction, right? So it's only gender, oxygen, and condition. Those are significant. That's why we interpret those. Others, I mean, technically speaking, you can interpret the other non-significant predictors, but I just don't like it. You just say like, it's like, that's how it is interpreted. And by the way, it's just not significant predictor. So it's, I don't like that. But I kind of always ask my students to interpret only significant ones because they matter. Others essentially can be dropped from the model. You can just rerun the model without non-significant predictors. And so how would you interpret it? So for gender, you compare males versus females, right? For male runners, the estimated average pulse is so many units lower, right? Because it's a minus, lower than that for females. Oxygen intake, it's continuous. So as oxygen increases by one whatever unit, right? The estimated mean pulse, right? It's E hat of pulse. So it's estimated mean pulse. It decreases because it's a minus, coefficient is negative, decreases by 0.9 whatever units. And condition, it's kind of tricky a little bit because we have three conditions: treadmill, like indoor, outdoor, track. So basically, as the condition number increases by one in a sense, right? So as you go from treadmill to indoor track and to outdoor track, the estimated mean pulse increases by so and so many units.
I have a question about the condition.
Uh-huh.
So I'm a little confused. Like if you look at the long form data, there's no particular thing that says condition.
No, you did. It's no, we have a separate variable. It's called condition.
Oh.
Look in the code. No. We did compute this. Where is that fitness here? I increased the font while you were in the increase the font. So now it's here. Condition. We create condition. If like pulse 1, then it's 1, 2, or 3. It lives like outside of the long form data set. Okay. If you want, you can edit, right? You can just say like this when you're assigning it, right? You just say long form data and make it part of that data set. That's fine too. But like, for example, in Sas, variables cannot live outside of data sets, but in R they can. So there's no point really of making condition part of the long form data set, but you can. That's fine.
Okay.
And yeah, so this is how you interpret things, right? And finally, you use for prediction, say 36-year-old, blah, blah. I always ask students to compute by hand so that they understand exactly what's happening. Like you take the fitted model, you plug in the values, you compute those, and you get something. So it's 143.34 something. And then you run this in R. So basically in the, like a new data, gender is 0 because it's a female, age 36, oxygen 40.2, runtime is 10.3, condition 1, it's treadmill, condition 1, and level equals 0 because we want the random variables like U1 and U2 assume value 0. They're mean 0. And the prediction is close enough, and that's good enough. What's happening, the discrepancy, it's actually, why is it so? Because look, the R outputs 3 digits here, right? I think you can output more, but even if you limit to like 5 or 6 digits, it actually uses more digits in calculation that it displays. So in R, this is kind of more accurate prediction in a sense than what you do by hand. Because by hand is a round off error. You already rounded each coefficient to 3 digits.
May I ask a question?
R uses like a lot of digits for calculations. Yes, question, sorry.
There's assumption that the gender column has male in the model.
Yes, male, yeah, male is 1, female 0.
but in the data set, it is F and M.
M and
how
F.
it is plotted,
Let
how
me
it is plotted within R.
Let me see where I assign it. You know, it just by itself. It's actually assigns by itself, right? It's on the
Yes.
output. You see here, it says gender M.
Oh, output. Yeah, thank you.
Yeah, so if you're happy with this, if it's okay if you model males, then that's fine. You can actually change. You can change the reference to females if you want. I mean, right now reference is female. You can change it to male if you want. It's with the re-level function. I just didn't want to like do it in here. But like in the book, you'll see that it's a re-level. That's what we do with the students. We try to match Sas and R. So we do a lot of re-leveling, changing the reference levels for a lot of variables. But basically, you pick it up only on the output. That answers your question, right?
Yes, thank you.
Mm-hmm.
So can you remind us briefly what that control equals LME control?
It's basically so if without it the model might not converge. It'll just say like, oh, I don't want to converge. It's I don't want to elaborate on that because it's you have different options here. If you're interested, you can just like Google it. It's basically making the model converge.
Okay.
It's basically what is happening is that you need to estimate a lot of parameters, and the data set is not large enough. I remember we have only like, was it like 27 or something, or maybe more? But it's a smaller data set. So it might be that just the model does not converge. Not all parameters are estimable.
Okay.
But typically, when you apply this model, I mean, hopefully you'll have a bigger data set. And then it will converge.
Okay.
Especially as like sometimes say with the random slope and random intercept, it does not converge. But if you remove random slope and leave only random intercept, it will converge. I mean, technically speaking, if it's not converging, meaning that, I mean, you need a bigger data set. I was using smaller data sets so that I can present them in my book and like something manageable. But in real life, your data sets are probably larger and it will converge. Should we move on? Should we take a little break? We should be coming from a break right now, actually, according to the schedule. Sorry, question.
Hello, Dr. Olga. I have a question. How did you determine to keep the random effect for condition and intercept, or remove the random effect?
It's actually a good question. It's these estimates are like the random effect estimates are estimates of the sigma coefficients themselves, right?
Yeah.
But it doesn't tell you if they're significant or not, right? If they're
exactly.
So it's in R you can do I think it's called intervals. I know that in Sas it gives you p-values for testing if it's 0 or not. But look, here they're pretty large in value, right? The values are pretty large, so you can believe that they're significant. But I also, again, I wanted to omit it and not to mention it in the talk, but I think you can just do intervals. You can say intervals. Look in my book. In the chapter 8, it says intervals, so it will give you confidence intervals for those coefficients. So if confidence interval covers 0, meaning it's 0 is a plausible number, it can be 0.
Right, not significant.
Yeah, so it's instead of p-values, it outputs confidence intervals. I just didn't want to like
I'll check.
Presentation more difficult with the
Thank you.
So how did you know which one to pick as the condition? Can you explain that again? How you knew which one to pick?
Oh, they all are significant, okay, in this case. It's typically, so what is, like, say, if, say, random slope is not significant, then this that standard deviation will be very small.
Right.
And also the correlation coefficient should be also small, because basically U2 does not exist.
Right.
So if
okay, now this theory makes more sense. Okay,
yeah,
going.
but you see, in this case, they're quite large, just even like by looking at them, right? They're large numbers because the correlation is like almost -1. So it's really a strong negative correlation there. So it's, yeah, so, but if I mean, if you want, you run intervals and it will give you the confidence interval for each coefficient. And then you can decide. But you know, it's like, even if something is not significant, I would still leave it in the model. Like 20 years ago, I used to teach students like, oh, you have to like reduce the model to only significant predictors. Like everything should be significant. And then I started working with health sciences people. And I've noticed that there are a lot of like, there's some variables they want to force into the model, regardless if they're significant or not, because they are interpreting the coefficients in the presence of all these other variables. So then I kind of slapped myself on the wrist, like not to tell students, just to reduce to significant. It heavily depends on the field and on the situation. You have to like tune in with your, like with the field like you're working in, see what your like a client wants, right? And then so I started leaving everything. You see, like in this model, I'm not throwing away all insignificant predictors. I'm leaving them in the model. And likewise, if you're like, for example, U2 is not significant, I would still leave it there. It will just take away a little bit of the like on itself, right? All the estimates, like when you estimate the coefficients here for U2, it will take a little bit of like.
Correct, you're chopping the tail, right?
Exactly, yeah. So it's, I mean, it depends on the preference. In regression analysis, there's no like black or white answer. Like there's no correct solution in a sense. It's always a matter of preference.
Dr. Olga, is this a good time to take a break?
Yes. We need to take a break.
So why don't we come back at 25 after?
Okay, that's fine. So basically, this is where we stop. Now, this is kind of the second half of this workshop is on. So there must be alternatives to this model that we just learned, right? Mixed effects model or random slope and intercept model. And an alternative would be what is called generalized estimating equations. And remember, I told you we're only looking at the distribution of the response variable. And in this GE approach, it's called GE, generalized estimating equations model. So what is happening is, so the response Y, right? Normally distributed. The mean is like before, right? The expected value of Y is just random, like the fixed effect terms, right? And time is a fixed effect predictor. But what is also like, so we don't have now random slopes and intercepts. And we don't have random error epsilon anymore. What we do, we model the correlation matrix for Y, for the response. So basically, all the parameters, like before we had like 4 different sigmas. Here we will have parameters of this correlation matrix. It's called working correlation matrix. And so in a sense, it might be even easier to think about it in this term, right? Like the response variable is normal, mean is so and so, and correlation matrix is so and so. Because remember, when we interpret, when we predict, we use only the estimated mean, right? We forget about all the other coefficients. So in this case, all these other coefficients will be in the correlation matrix. And what is typically considered, like different types of correlation matrix, there are 4 types. I believe R considers only 4 types. I think Sas considers one, like it can fit one more, but R can fit this 4. But 4 is enough. It's a good number. So the most general working correlation matrix is called unstructured. Unstructured meaning that all correlations are different. Now, this is what it is the following. It's kind of important to understand what's happening here. So different individuals, the observations are uncorrelated, right? It's only within one individual, within the same individual, the observations are potentially correlated. And this is a correlation coefficient for, correlation matrix for one individual. Here I have P's, like P time points. Before I mistakenly had K, right? Change it to P. So you have P time points. And what is it? So on the main diagonal, you have ones, right? Because it's just by definition, right? Observation is the correlation between, like, it with itself is 1, right? But say alpha sub 1, 2 is the correlation coefficient between observations at time 1 and time 2. At time 1 and time P. And it is symmetric, right? It's the correlation matrix is symmetric. Now, because all these coefficients are different, so basically correlation between baseline and 3 months, baseline and 6 months, baseline and 24 months, they all are different numbers. And a total number of coefficients here, you can compute. This is P times P minus 1 divided by 2. So if you have like 4 time points, right, it will be 4 times 3 over 2. It's 6 different parameters you have to estimate. So this is kind of resource consuming model, right? Like if it's so many parameters in unstructured model, but if it can be estimated, if the data set is large enough to estimate all those parameters, most likely that's the best model to use. Right? Now, more frugal model is what is called autoregressive. It has only one parameter, alpha. And what it is the following, and it's kind of logical because like a physical meaning of it. What is it? Just think about it. This alpha, look, on the downward diagonals, you have alpha and then alpha squared, alpha cubed. So what happens is that as time progresses, like it's, say you're comparing time 0 to time 1, time 0 to time 2, time 0 to time 3, these correlations become smaller and smaller. Remember, alpha is a number between -1 and 1, right? It's a correlation. So if you square it, it becomes only smaller. So it means that the further time points you take, the smaller the correlation is. And that's very logical, right? So basically, like LDL level at time 0 and LDL level at time, like, say, 3 months, 6 months, 9 months, they should not be correlated the same way, right? Correlation should decrease as more time passes between time points, right? And that's what we see here in this autoregressive correlation matrix. Correlation becomes smaller and smaller as time progresses. Now, the third working correlation matrix that is useful is what is called compound symmetric or exchangeable. It has one parameter, alpha. It is basically, it's alpha everywhere, meaning that the correlation is fixed. And if you have longitudinal data, that's not very really plausible matrix, right? Because you do expect that correlation decreases, right, as time passes. but it is very useful when you're looking at conditions, not time points, but different conditions. Because like running on a treadmill and indoor outdoor track, why should they have different correlation, right? You kind of assume that correlation is the same, right? Between running on a treadmill and indoor track, running on a treadmill and outdoor track, the coefficients, the correlations will be the same. So it is really useful model when we're talking about different conditions, because there, like a priori, we cannot really assume that. I mean, there's no reason to assume that the correlations would be different between different conditions. They all should be the same. And lastly, the last model is what is called independent, meaning that all observations are independent from each other. And you can just do linear regression. So within the same individual, observations are not correlated. So there's no point of running this mixed effect model. You can just run a linear regression model for normal response. Now, how to pick which model is better? Because like we're fitting 4 models, how to tell which one is better? Well, it's, I don't want to like give you the formula, because in this case, the formula, I mean, usually we say like, oh, show me the formula, right? But in this case, even somebody shows me the formula, I won't be able to say what's happening. So I kind of decided to add it all together. But basically, there is a criterion. It's called quasi likelihood under the independence, or QIC. Everyone calls it like QIC criterion. And that QIC, so R outputs QIC value, and you're looking for the smallest QIC. So the model will be fitting 4 different models with unstructured working correlation matrix, autoregressive, compound, symmetric, or independent. We will be just comparing QIC, and the smallest QIC wins. So that would be the best fitted model. And if there is a tie, I mean, typically say compound, symmetric, and independent have the same QIC, just because alpha is so small that it is almost like independent. So it is the same model. You just pick one, pick easier model. Like say, if compound, symmetric, and independent give you the same QIC, I would just pick independent, simpler model. And once you fit the best, like once you pick the best fitted model, then you can run it again and estimate the interpret estimated coefficients and use it for prediction. And let us go back to our example. It was like LDL example. So this is what you do. It takes GEPAC library. In fact, there are many different packages, many, and so it basically I remember programming in all of them, and I kind of picked this GEPAC as the most reasonable. It gives you something that we can understand right away. So first we fit unstructured. So this is what you say. I'll just call it UN, unstructured fitted model. GEGLM, generalized linear model. So LDL, you're regressing on gender, age, and months. ID, you have to say what ID is. ID is ID. Family is Gaussian, like normal Gaussian. And link identity, because it's not, link is the function that connects, relates the mean response to that linear regression. And in this case, it's just identity, right? It's not, we're not exponentiating or anything, just identity. And this is core structure of the correlation, core structure, and unstructured. We want to try unstructured. Very often it just does not converge. It's not large enough data set, too many parameters that we want to estimate. But if you're working on a bigger data set, it should be okay. You should be able to estimate. And this is what you see. You see coefficients. So these are beta coefficients, right? We're looking at p-values. Like months is not significant in this case. It's only age and gender. And these are the estimated correlation parameters, because you need to estimate all these alphas. We had zero, like zero, right? and then 6, 9, and 24. So you will have alpha like 1, 2, 1, 3, 1, 4. And then 2, 3, 2, 4, and 3, 4. So with 4 time points, remember we calculated, you have 6 parameters. So here they are. So those are the estimates. And I don't think it estimates p-values, just standard error. You can potentially, if you really want, you can compute some kind of like take estimate, divide by standard error, and look up in like t distribution or something. But I just don't want to do it here. But look what happens. Look what happens. It estimates everything, and we think we're okay, but model is not reliable because one estimated correlation is, if you take a closer look, it's actually above 1, and it cannot happen. And it means that it's not really, it should not be used. I think it's just formally estimated, right? But we know that correlations are between -1 and 1. They cannot be above 1. So it's not really, I wouldn't really use it for like prediction, this model. So even though formally it estimates, it ran, right? It converged. The estimate of the parameter is not really reliable. So we will just put it aside for now. And let's move on to the next one. So the next one is autoregressive. Looks like this, right? And so like these are the coefficients, the estimated coefficients. See, that's better because now with gender, age, and months are all significant. That kind of looks better to me, right? Looks more reliable model right away. And then the estimate of alpha is 0.701, which is also reasonable, right? So that's so now we started noting what QIC is for the autoregressive models. You have to request QIC value, and in the library mu m in. So you need to use that package and request QIC value. So that's 123. So when you see that it's kind of reliable model, note the QIC value. And let's feed the next one. So it's a compound symmetric. In R, it's exchange. It's called exchangeable. Like because you say correlation structure exchangeable. So maybe it's just more appropriate, like an R, just say exchangeable matrix. But I think it's more common name is compound symmetric, so I'm just like using both. I mean, it's easier probably to be flexible, use both names. So here are the estimates. They're slightly different than before. Remember, we had like 90 point. This is slightly different. They all are significant predictors. And this is the estimate 0.58. But remember, this is a longitudinal study. So you don't really I would be surprised if this is the best model, because we do expect logically correlations to decrease over time, right? As more time passes between visits. So I wouldn't say that that should not be the best model. And indeed, if you run QIC, right, it's worse than the autoregressive model, right? Autoregressive was 123, this is 126. So even though it fits and everything seems all right, it won't be the best model. And finally, the independent model, right? You just say independence and know that it's independence, right? Not independent. Independence, right? CE at the end. And look at it. The coefficients are actually very close to what the compound symmetric had, right? And QIC is the same, 126. Yeah, you see, even exactly the same. So basically, it means that this alpha is very close to 0 from statistical point of view, because these coefficients do not change if you use compound symmetric or you use independent working correlation matrix. The estimates of beta coefficients don't change. So this is, even though it converges and it's kind of a good model, it's not the best model. So the best model, according to QIC, would be autoregressive. And so that's what we do. We say, aha, that's the best model. Now we can maybe fit it over again, look at the estimates, write down the fitted model, write down, this is for practice, I wrote down the working, like estimated working correlation matrix, because it will be like alpha, alpha squared, alpha cubed. Alpha cubed meaning like there is a one time point in between, 2 time points in between, and 3 time points in between. So if you have 4 time points like 0, 6, 9, and 24 months, right? There are 4 time points. So in a sense, it ignores that those are so and so many months. What it takes is just visit 1, visit 2, visit 3, visit 4, and computes correlations. So the correlation between visits that are 1 time point apart, like 1, 2, 2, 3, 3, 4, those correlations should be 0.7. Those time points which are two time intervals apart, like visit 1 and visit 3, visit 2 and visit 4, the correlation should be alpha squared, 0.49. It's smaller. And then you have also visits that are 3 time points apart, visit 1 and visit 4. So that would be alpha cubed, right? The correlation coefficient will be even smaller. So this is how it is, how it works, the estimated working correlation matrix. Now, predictors are all significant, gender, age, and months. Now we can use it for prediction, for interpretation, and for prediction. So interpretation, you just look at those estimated coefficients. The estimated mean LDL for men is that many points lower than that for women. A 1 year increase in age, the estimated mean LDL increases by 1.032 points. And for months, for every additional month in the study, the LDL, like estimated mean LDL, decreases by 0.92 points. You can compare with that first model, with the mixed effects model. We had something very, very similar. The coefficients were not exactly the same, but like the direction, the magnitude were close. So this is kind of an alternative to the mixed effects model, but it is based on what is called generalized estimating equations. They actually, those equations are used to estimate the parameters of the model. You actually physically write down some estimating equations, and you solve them to produce all these estimates. So that's why it's called a generalized estimating equation model. And then finally, you just plug everything into the model and estimate. I believe we had like 136 something, and here it's 137. For some reason, R sometimes gives me integer value, sometimes it gives me decimals. I don't even know what it depends on. I mean, you can always round it. You can request more digits if you want. I just didn't bother. Okay, so this is it. This is it. That was example. So here is your exercise. So you go back to your fitness, right? For like 3 different conditions. You will fit GE model with unstructured, autoregressive, compound symmetric, and independent working correlation matrix. You output QICs. You will find the best model, best fitted model. Remember, those are conditions. So my suspicion is maybe compound symmetric, like a constant alpha might be, but I'm not so sure. And so that might be the best model, but I'm not so sure. And then also pay attention, the unstructured might converge, right? But it might give you suspicious estimates. And so then for the best fitted model, you will write the fitted model. You will estimate all parameters like I did. You tell me what the working correlation matrix is. And then you will talk about significance. and prediction. And once again, I let me see what. So the file will be that fitness G exercise. Don't look at solutions just yet. And again, I created a long form data set for you already, right? So then you can just hit the road running, like fitting the, like answering all these questions. Right? Okay. And use this, like the example here, you just like, feel free to open the example, just copy and paste, right? Modify the coefficients to save you some time. Modify the like predictors in the response. Okay, John, all yours. Put people in the separate rooms.
Dr. Olga, how long should we give them?
I don't know, 7 minutes. No, how much behind the schedule we are? Technically, you have 2 minutes to do this, right? Like 7 minutes. Then, no? 7 minutes should be enough.
7 minutes.
7 minutes. Copy, paste, modify the variable names.
Okay. We'll send everybody to the breakout rooms. Here we go.
And let's look at it. So did I intrigue you, first of all, by saying that you have different conditions, right? So which one of this, like, of the 4 matrices should be the best? I mean, logically, it might be compound symmetric, right? Because it's a constant correlation coefficient between the 3 conditions. But we will see. And also, I said, like, pay special attention, like, if unstructured is estimated, but what again, it's like if it's not reasonable estimates. So let's see. Did we get any of that? So it's unstructured, right? You fit in with unstructured. And so there are coefficients here, p-values here, and these are alpha estimates. We have only 3 conditions, so we really have only 3 parameters, right? Condition 1, 2, condition 1, 3, and condition 2, 3, right? And all these are fine, right? They're not beyond -1, 1. So they do look good. And your output, so when then it's reasonable, so you can estimate like output QIC, and it's 72.91, and remember that number. Then you fit autoregressive, right? Kind of simpler model, only 1 alpha, and QIC is 72.2, so that beats the unstructured, right? Unstructured has higher QIC. So far, autoregressive is better. And then you run compound, and look, compound has the same like fixed, oh no, it's slightly different, right? Like those, watch those coefficients, they change slightly, right? And not like a different alpha, they all are negative. No, this is positive alpha. And for compound symmetric, it's negative alpha. But QIC is the same. And finally, you fit independent, so alpha is 0. And QIC is again the same. And it means really, it means that it's not a good enough example, really, right? Because of these 3 models, autoregressive, a compound symmetric, and independent, they're all equally like well-fit models, and you just pick the easiest, which is independent. And it means really that you can just model data as independent, right? Even within the same individual, observations are uncorrelated. And I mean, you can see here, alpha is negative, here is alpha is positive, but in both cases, they're very small. So like from statistical point of view, they're equal to 0. So we can just use independent, even though it's like, I mean, it's not ideal example, right? Because we hope to see something where we really model data is correlated, but it looks like you don't have to. You can just run independent covariance structure. And that's what we do over again, just to illustrate. So now we're focusing just on the beta coefficient, estimated beta coefficients on the p-values. Runtime is not significant, and age is not significant. Like if we're judging by like at 5% level, so we can just say that gender, oxygen, and condition are significant predictors at 5%. And the fitted model will be like the estimated mean of pulse. You can compare it to what we had before, right? In the mixed effects model, it should be something very close, should be similar. And the working correlation matrix will be for independent observations.
Dr. Olga,
yes.
Does that imply that the mixed effects model wasn't necessary then for this particular set of data?
No, I think it was, because all these estimates were no, I think we had a good valid mixed effects model, right?
But does this result imply that you said even the correlations within the individuals weren't?
Yes, but it's not, these are not large enough data sets, I would say.
Mm-hmm.
So things happen. It's a small data set. You would really want a bigger data set.
So to follow up on his question, we can only then say within the range that we've measured, it's not needed, but it could be outside that range, outside that sample population that we measured, right?
It could be, but this is just an illustration.
Yeah, right. That I know. I was just trying to make sure I saw.
Yeah, but my gut feeling is that if you take a bigger data set, not like 27 people, not like 36 people, but like 70 people, 100 people, not humongous data sets, but not small either, you will have much more meaningful models.
How big of a data set in terms of like memory would you think would be big enough? Would you need like a gig?
The rule of thumb is 10 observations per parameter. Like in this case, how many parameters you need to estimate? Like 1, 2, 3, 4, 5, 6 plus alpha 7. So it should be 70.
Oh, because I was thinking like plus the correlation, then you would have to square that, and you would need like at least 4,900 or something.
Well, no, that's a very big. I would say 70, 80. Like say if you have 70 people with 3 time points or 3 conditions, that's good enough.
Okay.
So we have like 27 people, 35 people. That's a small data set. But I mean, this is just for illustrative purposes, right? Like you pick the model that has the smallest QIC, see that it fits properly, right? Like makes sense. What like the estimates that you see, and I mean this is actually happens quite often that autoregressive and compound symmetric and independent give you this, like it's the same model really. So once you feed it, you use it for prediction, right? We know how to do it. Males are lower than females. Oxygen intake increases by 1. The pulse decreases, like the estimated mean pulse. And from condition like 1 to condition 2 to condition 3, the estimated mean pulse increases by so and so many units. And then use it for prediction. Like we did that before. I think it was like 143 or something close. And once again, like R rounds it. I mean, for me, it might be your R doesn't round, or you can request more digits. I don't know. I just thought like, okay, 143 is good enough. But like but there will be always like slight discrepancy between what you compute by hand and what R outputs, because R uses more digits after the decimal point. So this is it. So what we learned actually 2 alternative models, right? Mixed effect model, also called random slope and intercept model, and GE, generalized estimating equations model. Which one is better? We have no way to compare, right? Because that QIC compares within, like between different working correlation matrices. And for mixed effect model, you can, I mean, you can see like if the model has a good fit, if it has significant predictors. But we don't really compare between like GE model and mixed effect model. We don't have like a easy criterion to use. But in general, we've already had that discussion today with someone. There is no like a black or white like correct answer in when it comes to regressions, right? You try different regressions, see um, uh, which one you like more, basically, right? Like you can have um, a training set, right, and a testing subset, and see which one gives you more accurate results, which one you're happy about, which one is easier to explain. So it is always like this with the regressions, right? I just give you several methods of like running regressions in this case, and then it's up to you like which one you like more. Now I have another exercise, and we actually scheduled like 30 minutes for it. Now we have like 25 minutes, just additional exercise. And it's a weight loss data. Again, it's like health sciences data, but that's okay. I don't have to like explain difficult terminology or something. So in this case, you have two groups, intervention and control. You have gender. You have typical length of daily exercise in minutes, like 30, 40, 50, 15 or something. And then BMI at the beginning of the study, like time 0, and then at 1 and 3 months afterwards. And then everything is like the data are in that file. We'll open it in a second. And what I want you to do is basically everything, right? Everything that we have studied today. So you want to verify normality, right? You want to run random slope and intercept model, see which predictors are significant, interpret those, right? Also, very important question here would be: is the intervention group doing better than control? Because you're testing something, you're testing the intervention, and the biggest question here is the intervention working? So that you will have to be answering those, right? So basically, you need to say if the group is a significant predictor, right? And see also that intervention is really doing better than control. And then you want to compute something for like predict for something, right? Use the model for prediction. And then you run GE model with unstructured, autoregressive, compound symmetric, and independent working correlation matrices. And then you pick the best model and do the same as above, the same thing, right? See which predictors are significant, write down the model, interpret significant regression coefficients. Again, asking yourself, is the intervention working, right? And then you predict use the model for prediction. Okay, you have 22 minutes. Should be more than enough. John, all yours. 21 minutes.
Okay, I'll send people to breakout rooms. Here we go.
So that's additional exercise. So let's look at the solution then. That's kind of the last thing that we do today. So what you were supposed to get, you were supposed to get like a histogram looking like this. P-value is 0.22, so that's a good p-value, right? And meaning it's normal data. So we can apply our models to that. So the first one is random slope and intercept model. Once again, all this sigmas, right, and rho And again, I mean, you can do like interval. It will produce the interval estimator, but I just didn't want to talk about it today. Didn't have time. So there's like large values, right? Just look at like the absolute values. They're pretty large, right? So that's good enough, meaning that it seems like the random slope is needed in this model. And so these are the estimated coefficients. Look at the p-values. Looks like the intervention is not significant. So the group is not significant. And so is gender. So the only significant predictors are exercise and months. So really, in this model, seems like the model tells us that the intervention is not efficient. And you write the fitted model, right? Just like carefully write down the coefficients. So group is intervention that is modeled, right? So intervention is 1, control is 0, gender M. So we're modeling indicator for male, right? So male is 1, female is 0. Exercise is like the time spent, like minutes of exercising per day, and then months into the study. And all sigmas must be present, like all this estimated sigma rows you should write it down. Now, so typical length of daily exercise and months are the only significant predictors. And so then we would interpret those as, I mean, you just look at the coefficient. Yeah, so then exercise at number of minutes. So it's continuous as the like length of daily exercise increases by 1 minute. The whatever you were modeling BMI decreases by, like the estimated average BMI decreases by 0.039. And for months, like with each additional month in the study, the estimated average BMI decreases by 0.84, right? So because both coefficients are negative, and you want to see that decrease in BMI, right? With more exercise daily, you see the decrease, average decrease, and with the longer stay in the study, you see a decrease. But this is overall, right? This is for everyone, for intervention and control. And it seems that like group is not a significant predictor. So from statistical point of view, there is no statistical difference, right, between intervention and control, even though you can look at the estimated coefficient, right? Even though statistically it's not distinguishable from 0, but at least it is in the right direction, right? Because intervention has like average BMI lower than that in the control. I mean, this is actually, it should not be so discouraging, because no, BMI is not so easy to change. It doesn't change overnight. This study is actually, if you look back real quick, it's only 0, 1, and 3 months. You really start seeing change in BMI after like 9 months. I'm actually involved right now in a study. We just started seeing change in BMI at 9 months, because BMI change is like a long-term behavioral change in a sense. So it's like, it should not be discouraging. At 3 months, basically, it's just negative coefficient that's good enough. And what else? Prediction, right? Predicted like 30, BMI 30. That's a lot, but that's okay. 3 months into the study, it's a male patient in the intervention group who exercises 1 hour every day. And then you feed the GE model and look at it. So with unstructured, you got the estimate that is above 1. So that's not a reliable model. Forget about it. I don't even know why it estimates like this, because Sas just is not converging. That's it. Sas does not output estimates, but R, like sneaky R, outputs the estimates. And you really need to know something about those estimates, right? That those are correlations and they cannot be above 1. Now, so then we're really like looking into autoregressive, right? That gives a reasonable estimate. So we're noting QIC, compound, symmetric, and independent. But look, independent is not a good model in this case, right? So now we're choosing between compound symmetric and autoregressive. They gave us the same QIC. You know what you can ask maybe to output more decimals of QIC. Maybe there is a slight change in like in the first or second digit, but what I just thought like that's fine. So basically, if we're choosing between autoregressive model and compound symmetric is easier, right? Because you just have like alpha everywhere, meaning that the coefficient, like the correlation is the same. And in fact, just think about it, between like 0, 1, and 3 months, not whole, like you won't see much change in correlation really, right? In BMI, it should not change that much. So compound, I would just fit compound symmetric because of the two, it is simpler. Autoregressive or compound symmetric is simpler. And that's it, you fit, right? You write down the estimated mean BMI, and you write down the estimated working correlation matrix. And our alpha, the estimate was 0.887. So this is the matrix. This is within each individual, right? Over time points, like a 0 to, there should be 4 time points. Maybe I'm mistaken. How many time points are there?
Can you speak to that in the one model, the group was significant, barely, and then in the other model, it wasn't? Would that favor one model?
Wait a second, say it again. Which?
So the group in the compound symmetric is not significant, but it is significant.
Yeah, here it is actually significant at 10%. Yeah, that's actually, and the coefficient, the estimate is in the same direction. Yeah, that might be something to note, and that might be something that why you would prefer this model over the random slope and intercept model, because it does show some significance of the group predictor. But like, just give me 1 second. I think I made the mistake again, because how many time points do you have? I think we had only 3 time points, right? I think we had only beginning of the study 1 and 3 months. We had only 3 time points. So I kind of overdid it, I believe. I put extra here. Yeah, I think I overdid it because I did it manually, probably copying and pasting, because you have only 2 time points. So it is a 3 by 3 matrix, not 4 by 4.
But how about between the autoregressive and the compound symmetric? So you've got a very similar QIC score, but the significance of the group is different.
Wait a second. Is that different? Here, yeah, it is actually. This is independent? No, wait.
No, it should be there.
0.4. So yeah, this is significant actually at 5%.
Compared to
you're right. I mean, it depends on what you want, right? If you want to show significance of your intervention works, then maybe take out a regressive model, right? Yeah, you see, this is actually a good illustration because you have a perfectly good alternative, right? That this has a 5%, like kind of barely, right? Pulled by ears, 5% significance of the intervention. I mean, if your goal is to show that intervention works, you might choose this model. If you're just picking a simpler model, that would be compound symmetric. It has a 10% significance, right, of the group predictor. Either one. I mean, it's like then it kind of, I think in this case, it depends on the situation now, right? Like what you want to demonstrate. So the only thing it's a 3 by 3, it should be 3 by 3 matrix. Doesn't matter how many times you fix it. Okay, so that's how the estimated working correlation matrix looks like. And so daily exercise and months are significant predictors at 5%, right? I mean, you can talk about significance at 10%, that's fine. for group. I believe I talk about it here, right? Well, if you just like really restrict yourself only at 5%, right, then group is not significant. You can say it is significant. It is significant at the 10% level. And you can interpret it. So it is actually in the right direction, right? It's a negative coefficient. So the estimated mean BMI in the intervention group is lower than that in the control. And then for exercise, like the more you exercise, the less the like BMI is, right? The minus, and also more months in the study, BMI decreases. So that's fine in the right direction. And I don't know, I picked, I mean, you kind of brought up a good question because I picked just simpler model in terms of like the structure, right? The working correlation matrix structure will be simpler for the compound symmetric. But you brought up a good question because here it's like the group is significant only 10%. You might want to go with the more complicated working correlation matrix structure, right? But with a more significant predictor. It depends on the situation, depends on what you want. Maybe in this case, you don't want to see that the intervention worked, so you want to pick autoregressive then. But I mean, in general, statisticians are moving away from like just looking at the p-value alone, saying like, oh, okay, it met the 5% mark, so we're good. It's not really the way to do it, right? And the last thing we do is prediction. You know, I didn't like I can do this like open full screen, and we can just do prediction. Before it was like 30, I think in the previous model. Now it's like 29.7. And that's it. That's it. Thank you.